Hey everybody, Tom Cherry Holmes here with the FujiNet project, and I wanted to make what will ultimately be a very long video here, showing the entire process of creating a binding for a programming language using the Atari as the development environment, from start to finish. In this case, it will be for the Action programming language, and hopefully this can serve as a handy reference for building bindings for your other favorite languages on the Atari computer as well. This video is essentially divided into 3 parts. The first part is setting up the development environment and is arguably the shortest part of the video. The second part involves the creation of what we will call the NIO library, which will ultimately be the library that you use to do the communication with the FujiNet device. And the third part will be actually writing an example program, which we call Netcat, which is arguably the simplest terminal program you can make using the bindings that we create in the second part. First part here is, of course, setting up the development environment. I've already inserted my Ultimate cart into my system and turned on the power. It's waiting for me to select a cartridge. Once we do so, we'll go into DOS and format a work disk. So we'll go ahead and select Action, and because FujiNet has been cold started here, it will actually take and bring us into the FujiNet configuration program where we can set our disk slots. Right now everything is empty. Within a few moments, config loads, connects to the network, and everything is cool. On my SD card slot here, I have the zip file that you can get on Atari Age or in the GitHub repo of pretty much a lot of useful DOSes and disk utilities. It has a folder called DOS, which contains a whole bunch of pre-configured DOS images with FujiNet utilities already on them. For the purposes of development here, I am actually going to, just for the hell of it, we're going to use OSA Plus version 4. Why? Who knows? Just because. And because version 4 can use larger disk capacities, I actually need to take and set up a work disk, and we'll do that by going onto my local file server here. While I could put this on the SD card slot, I'm opting to take and actually put this on the network. And I will use new to create my Netcat Action work disk. And because OSA Plus likes large disk capacities here, I'm going to use a 360K disk for my work disk. Am I sure? Absolutely. We're going to put it in drive 2. And we're going to press Option and boot. And within a few moments, we'll find ourselves inside of OSA Plus version 4. And as we can see right here, since this is a FujiNet disk, it has all of the FujiNet utilities at our disposal. Right there, ready to use. If we go to drive 2, we'll actually see that there's nothing. The disk is completely blank and actually honestly cannot be used. So we need to take and prepare it, don't we? So we will go ahead and run config just to make sure that the disks are configured correctly. We'll see that we have a double-sided, double-density disk ready to go. And if I run init, we will take and initialize drive number 2. Disk is complete. We go to drive 2. We do a directory, and we'll find that we have 1417 free sectors ready to go. And that's all we essentially need to do to get our development environment ready to work on our code. We'll go ahead, and if we go to the cartridge, we will find ourselves in the editor of the action environment. The next part of this actually involves writing the library that will be used for network communication with FujiNet. Since Action is a high-level language, and it has complex data structures and can easily interface with machine language routines, it actually makes sense to write a library that communicates with the FujiNet directly over SIO. This keeps all of the routines self-contained within the program. They don't take up that much space, and they can be used in a variety of different contexts. You can put it onto a cartridge, you can make it a bootloadable disk, you can make it a COM file. It does not matter. So with that, let's get started. I'm going to go ahead and move my microphone over to my Atari here real quick. And here we go. Boom! We are now inside of the Action Editor. The Action Editor is a complete full-screen editor, which for its time was actually most amazing. I mean, especially when you think about it, when the majority of text editors that you had for other languages, even for languages such as Mac65 contemporaneously, still required you to type line numbers. It works just as you would expect a text editor to work. You type in some text, and there it is. You can type it in, you can delete it, and as you can see, the text editor itself is actually quite zippy. You also have the ability to take and do editor commands to do all sorts of editor manipulations. The first one we'll deal with here is to put the editor into insert mode, which is the way that I like to work. By default, if you type something and you try to type something over it, it won't move the other characters out of the way. It works in what's called replace mode. All of the editor commands start with Control and Shift, and many of them are mnemonic, so they're easy enough to remember. Shift Control I gets us into insert mode. If I press it again, it goes back to replace mode. Inside insert mode, and I type over some existing text, it will push that text out of the way for me, which is very handy, especially when you code the way that I code, where basically things need to be shifted out of the way. So in other words here, I'm going to show as you type, the editor will actually scroll to get certain things out of the way. So you can see on the left and right hand sides of the screen that the two characters on both sides are inversed to show you that there is text on one side or the other of a particular line in the buffer. In addition, many of the conventions from Atari Basic are also honored here. For example, Shift Delete will delete a line, and Shift Insert will insert a line. So with that in mind, we can already start to write the first lines of code. It's a good idea with action programs, especially libraries, to take and start off with comments at the top of your code indicating what this particular block of code is and its function. And as I start coding, I like to be sure and hit the caps lock key to get us into lowercase mode so that we can use both upper and lowercase letters. You can see the difference now. So there we go, a little description, put an authorship. There we go. And we can start off with our first action keyword. You'll notice that we use the semicolon here to denote comments, and a semicolon can actually appear anywhere on a line. But once you put that semicolon, anything after that semicolon is ignored by the compiler. We'll start with our first reserved word, which is module. Module tells Action that this is a discrete module of code, meaning that you can start using global variables after you specify the module keyword. And because coming from other languages, you might balk at the number of global variables and how variables are actually allocated in this language. But it was what was deemed at the time a necessary simplification to not only get the language to fit and run well on a 6502, which has a limited stack, but also to run as efficiently as possible. When you define a variable, it is given a static location in memory, which you can specify. And that means essentially, and there is no stack frame. And that essentially means that, for example, functions cannot be recursive. And in certain cases, you can't use functions as the arguments of certain expressions. With that said, let's take and start defining some of our first variables using some of the data types that you have available in Action. We need some variables for our proceed interrupt. FujiNet is rather unique in terms of Atari peripherals in that it actually uses the two heretofore unused interrupt lines, which are implemented but aren't really used by most Atari peripherals, to indicate to the Atari computer that the Atari needs to pay attention to something coming down from FujiNet, such as when new bytes need to be fetched, or when the connection state changes. We need some variables to not only take and patch in our interrupt routine that we want to work with so that we can indicate that we need to pay attention to something, but we also need to have variables to control the PIA control to indicate that we're ready to receive interrupts, and we need a variable for our flag. To define variables, you actually need to take, just like in other ALGOL-based languages, such as Pascal, and to a certain extent B, C, BCPL, etc., you have a data type. In this case, the data type that we're using here is called card, which is short for cardinal. Cardinal allows you to specify a number from 0 to 65535, which is convenient for doing things like storing addresses. Beautiful, huh? So once you have your data type, you need to give it a name. So we have our variable for the proceed vector that we're going to save. We have another card variable for the proceed vector itself inside the operating system, using the memory location specified by the operating system to hold such a value, 0202. we have the single byte for the PIA control register that we need to control to indicate that an interrupt has occurred, which you can get from the Atari hardware manual. And we have our trip variable. Following on from that, we need a set of variables to hold important status information. We need, for example, a constant for dvstat. And the reason for this is actually going to become apparent a bit later, but suffice it to say, we don't want the value of what is at 02EA. We want the value 02EA itself to be dvstat, so we can easily reference it. In addition, we also need a byte for the extended error that actually occurs at 02ED. Finally, we have the heart of most of everything that we need to do in this binding, the device control block. Inside the Atari operating system, there is a fixed location of memory that the operating system uses when you want to communicate with the SIO device. Inside it, you put such parameters such as the device you wish to communicate with, the command you want to send, whether or not you have any payload, in which direction, how big that payload is, and up to 2 auxiliary parameters that you want to be able to take and pass along with the command for special purposes, as well as how long this command needs to take, and finally, for any payload, any buffers that might need to be passed along with it. So we need to define those. Since this isn't a fixed block of memory, and Action has data types that match up quite nicely to what we need to do, this is very trivial. We need a byte for the device number. This goes at 0300. We need a byte for the unit number. This goes at 0301. 0302 provides us the command we want to send. And as we see right here, 0303 is actually kind of special. When you form an SIO command, it specifies the direction that a payload needs to go. Either 0 for no payload, 40 for peripheral to Atari, or 80 for Atari to peripheral. When the command is finished, this byte is reused to indicate the error of the serial I/O communication. We need a value for the buffer. We also need a byte for, we need a cardinal for the buffer because it's an address. We need a byte for the timeout. We need to indicate that this byte is actually unused. It may have been used at one point, but it's reserved now. And we need to specify, if there is a payload, how many bytes are in that payload. And finally, we're going to make a couple of variables that essentially point to the same place, but the variables themselves are two different types, so that we can deal with this value a bit differently depending on whether or not we want to treat the auxiliary values as a single 16-bit value or as two 8-bit values. And actually, it looks like I need to 304, 306, 307, 308, 30A, yep. Pardon me there. This first value treats, this first variable, deaux, treats the auxiliary values as a single 16-bit value, and thus we use card. We use byte for deaux1 and point it to the same place, and this gives us just the aux1 value by itself, without having to, and especially if you're used to dealing with values in BASIC when you're calling machine language programs here, specifying this as a 16-bit value here avoids you needing to do multiplication and addition to take and add the two 8-bit values together to become a 16-bit value, like you often have to inside of BASIC. Now you'll notice that deaux and deaux1, they point to the same place. Action is fine with this. The compiler will happily create the symbols, and they will be treated differently by the compiler. And they will do exactly what we want them to. Those are the variables that we need. We'll go ahead and save this as it is by, go back, I won't do that just yet, by pressing Control-Shift-W to write the file and write it out. nio.act. Here we go. Bam, 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 bam. Done. Great. Now let's take and write out the next little bit. The next piece that we need to write is actually the interrupt handler. And this kind of shows you a peek into how well Action can integrate with machine language code. And the way that this actually works, I'm going to type in the hexadecimal code on the left, the machine code on the left, with the assembler on the right, and we're going to take the hexadecimal codes and put it into an array and point the function pointer directly to that. You'll see in just a moment. The first instruction that we want to deal with is LDA01, because we want to take the value 1, we want to put it into whatever value that trip happens to be when the compiler figures it out. We'll see how we do this in just a moment. Finally, since we're done with this interrupt, we need to do a little bit of house cleaning, pull off the bits that were put onto the stack by the operating system back into the accumulator so that everything works as expected, and finish up the interrupt. That's the extent of our interrupt handler. All it does is, if an interrupt happens, it immediately sets the trip value to 1. And the way we implement that is as a procedure using the proc keyword. Procedure takes at least one argument, which is the name of a procedure. And since this is a bit of machine language code in an array, we specify it like this, with the contents inside these brackets. And again, we take the hex that I've done over on the left-hand side, and while we can put spaces between them, we don't have to. So 8D, and then watch this. I am literally going to take and put trip right here. And the compiler will happily take the address that that variable is situated in, put it inside of here, and thus allow me to specify a variable entirely within action and have the compiler do the right thing here. It's very seamless. So now that's the extent of the interrupt handler. Boom, done. Now we need a set of functions to actually enable and disable that interrupt handler. Again, the proc keyword, the name of the function, and any arguments that the name of the procedure, and any arguments that that procedure may have. Now I will stop here and state for just a moment that those of you that are familiar with Pascal may see this as familiar, as Pascal has a difference between what are procedures, which are functions that don't return anything, and functions, which are functions that can and do return values, even if you don't use them. Procedure needs to be terminated with, a proc block needs to be terminated with return. And the contents of this particular function, of this particular procedure, are very easy. We go ahead, we set trip to 0 to clear it. We use the vProceedSave variable that we did above, since it's global, and we set it to the value of vProceed. This actually saves a copy of the vector that's currently pointed to at vProceed, so that we can restore it when we shut down everything using disable proc. Then we take vProceed and set it to our interrupt handler, and the interrupt will now be used when it's called upon. But it won't be called upon unless we signal to the PIA that we are ready to receive an interrupt in the first place. By default, PIA interrupts are disabled, and it's your responsibility to turn them on for things that you want to deal with. We will use an OR to do so. And we'll do that by taking the value that's currently in PACTL, preserving it, but changing a single bit using the bitwise OR parameter here to turn on the least significant bit of them all, which happens to be the interrupt enable. Coming from C, you might be used to seeing the vertical brace be the bitwise OR. Here in action, it's %. And this is essentially all we really need to do for this particular function. We're done. We're ready to receive those interrupts. We're good. We're golden. Conversely, if we go ahead and do disable, for disable we clear the trip as before as well, and we set vProceed as vProceedSave, essentially reversing what we did in enable proc, and then we take, is that it? Yep, that's it. That's all we really need to do. Everything is done. We are good to go, and that's how we disable. So now we have enable and we have disable. Bam, bam, done. Let's go ahead, save that out. And let's go ahead and compile that to make sure that that's okay. It's a good idea to compile as incrementally as you possibly can, because as we'll see, if we get errors here in the compiler, it doesn't tell you what line numbers that they're on. So it's a good idea to take and build a little, compile a little, so you can have in your head where you are, and therefore you have a good idea of where your problem is because you just typed that out. Makes sense, I hope. So the next thing that we need is a proc to call SIOV. And all we really need to do here, once we set up the device control blocks that we've set up, we'll see it here in a minute, is we just need to JSR to SIOV. That's it. Jump to that machine language subroutine that already exists in the operating system ROM. And for action, this is really easy to do. All we have to do is create a proc that points directly to SIOV. And this is simplicity itself. If you define SIOV with an equals like this, just like equals in the case of defining a variable gives a pointer, this basically compiles into a JSR SIOV going to that function, bouncing back. And that's all we have to do to call SIOV. Done. And we're done. And this leads us to our first utility function. We need a particular utility function to, given a device spec, for example, we need to be able to figure out what the unit number is so we can pass that into D units so we can test the various different device units. We could make this simple and say that the unit is always 1, but maybe there's a reason for us to specify another unit. It's easy enough to take and write a function to parse this, because all we're really interested in is where this colon is at the first part of the device, and whether or not there's a number there or not. Whether, is the colon in the 3rd position or the 2nd position? That's all we have to worry about. And if it's in the 3rd position, like this, then we assume that this is a number from 1 to 8. We can safely assume this because really by the time we get to this point and we pass in a device spec, either the FujiNet firmware is going to accept it as a valid device spec and do something with it, or it's going to bounce back and say this is an invalid device spec. So all we have to worry about is just passing in a valid unit number and providing a default unit number of 1 when 1 isn't present. This is easy enough to do. And since this is our first function, and not only our first function, but our first procedure or function with parameters, we'll see how we do that as well. I have a particular convention that I use to document my code to indicate parameters and return types. In our case, we use a device spec. We use a name here like param or return, the variable that we're going to do, and the description of it. And there we go, our nicely documented function. Get into the habit of doing this. It's a very good thing to do. Since this is a function, we needed to give it a return type of what we're going to return. And we're going to return the unit number as a byte to match this variable up here. Nicely done. So byte, and it's a function. and it's called getUnit. And it takes a parameter. In this case, this is the first time that we'll see an array of bytes. You can call it a string, it's just an array of bytes. And it's called DS for device spec. And we're going to return a unit number. We need to go ahead and define that variable inside our action code here, because otherwise the compiler is going to throw a fit. Now, coming from C, you might be tempted to go ahead and set a default value here, for example, to make the code a bit simpler. Do not do this, because you'll notice that we're specifying a data type here, and we're specifying a variable, indicating that to the compiler that this is now a pointer to somewhere in memory. In this case, memory address 0001, which is most certainly what we do not want. So just leave it uninitialized. And parsing it is actually simple enough. If you're used to if statements from other languages, these work similar. You have a keyword, if, followed by the expression that we're going to check first, which is the first major position for a colon. Action specifies single character literals, ASCII literals like this. You do an apostrophe followed by the character that you want to check. And this is different. Let's say this is checking for the character 1, whereas this is checking for the number 1, or checking for the number 1, etc. So we're checking for a colon here. If there's a colon here, then we go ahead and put the end of the block here. Because the Atari does not have curly braces like you see in C and in some other languages, they opted for instead to use the inverse of the start of the block to denote the end of a block, like you see in some other languages like Bourne Shell, for example. If there's a colon there in the second position, then we can safely assume that the unit number is 1. Else if is specified in this manner. Else if there is a colon in the third position, then we do a little calculation to determine that unit. Now, you might think, well, we just grab DS2, right? The number into the second position, but that's not a number 2. That is the ASCII value of 2, which is 32 hex, which is not what we want. It's always going to be 30 hex 30 more, or 48 more than the value that we actually want. So the solution is very simple. We take the value and then we subtract hex 30 from it to get us our nice neat integer value, byte value. Boom, done. So now we have that. Finally, if all else fails, unit is still pretty much 1. There are other ways to write this particular construct, but I did it like this, basically to show in a full way how the full form of the if statement, how it works. Finally, we return the unit, and all is well. So there we go. In fact, what we're actually going to do is we're going to save what we have right here. We're going to compile it to make sure that it's okay. And then we're going to write a little test function to make sure that everything is acting as expected. To do this, we are actually going to, now that we've written the file, we're still in the editor. We need to go out to the monitor to take and get to the compiler. To do that, we hit Control-Shift-M. I'm going to warn you ahead of time, you're going to hear a very obnoxious beep. Get used to this beep. It happens every time the monitor prompt is displayed. Control-Shift-M, and we find ourselves out into the monitor. At this point, we want to compile what we have, so we press C to compile what we have. And if there are no errors, you immediately come back to the monitor prompt with the extra beep, letting you know that the compile is finished. All is good? Great. But we need to test it and make sure that this function actually works as expected. The best way to do this is to basically write a function to test it. Now, actually, it's kind of interesting because what happens, the very last function compiled becomes the entry point for your program. This is in stark contrast to languages like C that have a specific function, named main or something similar, that functions as your program's entry point. No problem. We'll just kind of put one in here. So we'll call it test. It doesn't need any parameters. We're good. So return. And your entry point, technically, there we go, shouldn't have any parameters. Anyway, so here we go. Bam, bam, test. We will do, just to make sure, to really drive the point home, to make sure that this works, we'll do a simple hello world. And we'll compile it. And we'll run it. And as you can see right there, there's the test function running right there as it should be. Well, let's write some bits and pieces to actually test the get unit function that we did. Start with, we need to have a byte for the unit, and we need to test against it. Device specs are always going to be 256, so we might as well go ahead and just put it in there. In colon. Let's see, TCP. It doesn't matter. It just needs to be something. So, like there, we have our byte array for our device spec, and U equals in get unit, and then we can print the result using a library function called printB, which prints a byte value. And since we want to return on the end, we can go ahead and say print BE. Many of the input and output functions in Action follow this similar pattern. You have print followed by the data type, followed by whether or not there is an end of line character or not. If you don't want one, take it away. Boom, that sort of thing. So with that, this will give us an opportunity to test this function to make sure that it's working correctly. And this is essentially a primitive form of unit testing, and it's a good practice to have when you're writing code. Go ahead and write this out just for the hell of it. We'll compile it because we need to compile it to put it into memory so that we can run it using the R command. And we'll see that our unit number comes back as 1. This is good. And that's exactly what should happen. If I put in 1 here, the result should also be 1. What about here? The result should be 2. Let's find out. And you'll notice I'm just bouncing back and forth, making the change, not needing to save it, just bouncing it, making the change, compiling it, come back, run. And the result is indeed 2. Let's try 8. And looks like this function works as expected. We are golden. Fantastic. Dang, dang, bam, bum, bum, bum. Here we go. So, moving up, we are now followed by, let's see, our first major SIO command. which we need to get the status of the last network operation. We need this to get extended errors. We need to get this to get the number of bytes waiting for a read. We need this to figure out whether or not the connection has disconnected or disconnected or not. There you go. And we want to return the value into the place that the operating system sets aside for this purpose, which we call dvstat. All SIO devices pretty much follow this convention. dvstat, as specified before, is a set of locations left by the operating system starting at 02EA, 4 bytes long, and left there specifically for SIO devices to put their status information. Because of this, we don't really, the thing that we're going to return is essentially an SIO error if there is one. And we're going to pick up the status by literally referencing dvstat when we need it. So param is simply the device spec as before. Boom, 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 and there we go. So, byte func in status. Byte array, ds. We're going to return the value. And here we actually start to see how we construct a serial I/O transaction. We start by specifying the default device. And for this, we're going to do a constant called indev. And we're going to define that as 7.1. This allows us to define the constant as you saw before, and because this is actually done in the preprocessor, it doesn't have to belong as part of a module. The compiler will pick it up and simply substitute it wherever it's needed. And here is where we get to use our inGetUnit function that we did above with the parameter of the device spec that we did above here. Status dStatS, which is our data direction. Since this goes to the Atari, it's to the Atari. Debuff needs to go to dvstat, because that's the destination where it needs to go. "30-second timeout." Almost there. It's 4 bytes long. And there's not really any auxiliary values that we need to deal with. Finally, we can call SIOV and return the value that gets returned in dStatS. And there's our status call. You might be wondering where I get these particular values from, and for that, I'm going to switch to a slightly different screen here, showing our web browser. And as part of that web browser, we have it pointed to a wiki page, the FujiNet Platform I/O wiki here, which contains programming information. We're interested in the SIO commands for the end network adapter. And the ones that we're most interested in are the first few right up here up top. And let's look at status. You can see that many of these values are here, ready to be used. 7.1, da, 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 da. And you'll see that many of these match up with the values that we're doing here. D time low can be different. It can be whatever you wish. But for defaults, I'm using 1F. You can use however big you want to use. So now we have our status call. We can take and compile that. Let's go ahead and write that out because that's pretty much done. We can compile it to make sure it's okay, everything's good. And we can actually do a little test harness to see if it works. Byte error. Okay, error equals end status. We can grab the status, we can pull this, and finally we can also build bytes for DS4. So we have 4 variables here that basically point to physical locations in memory where the status state information is going to end up, because that's where we're asking it to end up. So the output that we're actually going to see is a combination of these values. Now I'm going to take and do a cut and paste here, and in order to do this, I'm going to position my cursor on the line. I'm going to hit Shift Delete, which will take that line and put it into the cut and paste buffer. You can do this as many times to pull in as many lines into the cut and paste buffer as you want, and then you can position your cursor over the destination and press Ctrl Shift P to paste them, like so. There we go, 1, 2, 3, 4, and if everything goes as expected here, we should see 5 values come back. Let's go ahead, I'm going to go ahead and compile this, but before we run it, I'm going to bring another window to this front of the screen here, which is our status, which is our debugger. Now, no doubt you have installed the FujiNet Flasher to get new versions of the firmware, but it also has an additional function as well. It can be used to literally show the debugging output from the firmware, which is very useful when you're writing software for the FujiNet. You do this by pressing the serial debug output. Now, because I haven't done this before, and because it's probably going to reset the FujiNet, it's a good idea to do this when you start. My bad. But that's okay. We can deal with this quite effectively. We can simply go back into the editor, make sure that I've saved my work. Then we can go back to DOS and prepare for a cold start in case this happens. I press the serial debug output button, and we are now showing the logs. And of course, it cold started the FujiNet here. No big deal. We deal with that just fine. We do a cold start and let it boot. But now you get to see the traffic. We'll go ahead and boot. And here we are back at our OSA Plus screen, ready to go. And if we go back into the cartridge, we'll find that we're back in the environment. And now I can use Control-Shift-R to read from drive 2 to pull back my NIO code. And we'll be back right as we left it. There's our test code. We go ahead and compile the result by going into the monitor. And when we run, we will see our status output. Boom. Right there. You can see the corresponding status. And you can see the corresponding output on the monitor window. We can run it again. And you can see our status information coming through just fine. Man, that's all we got to do. Awesome, isn't it? Go ahead and put you to the side for just a moment. And we will go back to the editing window. And we'll get rid of this little bit of test code for now. And move on to the next function. Of course, since I came back into action, I have to reset myself back into insert mode. And we write the very next function. The very next function is what's called inGetError. And this function is actually needed because SIO only returns a handful of errors, and those are the ones that are directly resulting from communication errors that might result. Maybe the command times out. Maybe the command is knacked by the peripheral. Maybe the command you can only return one of two possible states, successful states or unsuccessful states, from an SIO command, and that is either complete or error. If you return an error, you get an error 144. That's all you can do. So we need another way of returning more error codes. And we do that by using the fourth bit in the status byte, the fourth byte in the status return, to return an extended error code. And we need a function to basically extract that error code. If it's there, or if it's not relevant, we simply return back the SIO communication, which is most likely success anyway, making it a lot simpler to implement. So, back into lowercase. If SIO error is 144, then we ask that's it. Boom. And of course, parameters as always. And we do parameters in device spec, and we return. That's it. Boom. Okay. Now this is a function, and so byte func inGetError. Boom. And we're going to return an error. Now, this is actually simple enough. All we really need to do is check if that error is 144, and if so, then we get status and get the error from that status. Since dStatS points to the location in memory where the operating system puts that status information, we can simply reference it by the variable. If dStatS is equal to 144, then we do an nStatus, and we do an error is referencing our extended error, which again points to a fixed location, so we can just do this. Else B is equal to dStatS. So we return the SIO error. If everything is successful, you're going to get a 1 all the way down the line. And that's all we have to do. Boom. We will actually see that particular function being used in practice in just a moment. Now, we implement open. The end device is a bit unusual in that all of the logic, all of the magic is actually handled on the FujiNet, unlike a lot of other devices on the, unlike a lot of CIO devices on the Atari, where the handler basically does all the abstraction and does low-level calls over SIO to the target device. So we need an explicit open SIO command in this case, in which we pass over the device spec, have the FujiNet take care of all the details, and set everything up for us, and indicate whether or not that was successful or not. It takes a couple of parameters, the first of which is, of course, the device spec. But it also takes a translation value. This is basically a way to handle how end-of-lines are translated from input data and how they're sent back out to the output. If you're familiar with communication in say, modem programs, for example, you may recall that the character that a ASCII uses for the end-of-line and the character that ASCII uses for end-of-line are different. But that different systems can also have variations on what is used for the end of line. For example, some systems use carriage return and line feed, one right after the other. Other systems might just use line feed. Unix systems are common in this regard. And some systems, like the early Macintoshes, used carriage return only. To facilitate these differences, we have a translation mode byte here. 0 equals none, and that's equivalent to say either full binary, don't mess with anything coming in or out, a ASCII, whatever. 1 is carriage return, 2 is line feed, 3 is carriage return and line feed, with the added bonus of making sure that an extra character is added automatically when transmitted, and the extra character that you would get coming in is removed. So with that, we have in open byte array DS, and finally byte T. Boom. So we have our device spec and we have our translation mode. And this will pretty much be kind of a cut and paste, more or less, of the status call to start with. We'll go ahead, we'll put it back here, but we'll also paste it down here to get a head start. So we start off with, okay, boom, okay. So we do O for open. this command, if we actually go and have a little look at our browser window, we will find that, a second, go back here, go to open, and here are the parameters that we need. Since we are sending a payload to the FujiNet, we need to set this to FujiNet. Oops. Yeah, I had to insert, didn't I? Oops. Yeah. That was a shift on accident there. And the value needs to point to our DS, which is our device spec that we're sending in. Same timeout values. But we're going to handle deox a bit differently. Deox1, deox2. And this time, we're actually going to set deox1 by default to read and write. Again, this is just for simplicity's sake. There are other deox1 values you can use. Excuse me. You can tell I've been doing this for a while, and this is my third or fourth take today. So, with that, bam, 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 make sure we're okay, with the added difference that now we're going to use the nGetError function that we made earlier to return an appropriate error code. Now, I'm going to take and put in a particular piece of code here to turn on the interrupts automatically. If it's successful, which we know because we're doing an SIOB call here, go ahead and do that. Boom. And since we're not really using that yet, I'm going to go ahead and put that over to the side. The reason I'm doing this is literally because I do not want I do not want the interrupts to come on or come off so long as we're inside the action development environment. Because the action development environment will switch memory in and out and cause all sorts of problems as we do this. It's a mess, and it shouldn't be done that way. So we have to basically prevent any particular problems by going ahead, putting this piece of code in here, but commenting it out until we're done developing and making sure that it's enabled when we need it. But if we go ahead and put the interrupt enable inside here, then that is already helpfully done, and we don't have to worry about it in the target program. So with that, we have that, and we can actually start testing now. So let's save this as it is. Let's have a look at what we did going into moving our little browser window out of the way here for a moment. You can see our little open routine there with the little bit that we've commented out. And we're going to compile it. Oop, E equals X error. We have an issue here. Did I not? Oh, and that's literally because I did not define a return value. So, save that out. And very helpfully, when the error happens, the last error that happens, if you go back to the editor, it will put the cursor in the position where the error occurred. And the device spec. Okay. Oop. Slight mistake there. Making mistakes all over the place here today. It's okay. We'll get through this. So, again, compile, and we're good. Okay. Now we can take and write a little open routine to make sure that this actually works as expected. We're going to say error here, and we're going to do in open bam, and it needs to be opened. I already know this site uses carriage returns and line feeds, so we'll use the CRLF line endings, and we will get an error back from that. Print BE, the error, and Robert, your father's brother. Okay. Write that out. Good to go. Compile. Run. And right now we got a... So why did we get that? Let's see why. Let's see what happened. In order to do that, we'll bring back our FujiNet flasher window. And here we go. Let's have a little look. Oh, open. Nope. Back. Okay. So it looks like I need to do a little fix here somewhere. Let's find out. Let's make sure. Need to help to have the right number of bytes. We'll save that out. We'll compile that. We'll try again. And now we get a 1. Bam. All good. This works. Fantastic. We know this works. Groovy. Now we're going to go ahead and we'll keep this as it is right now because we're going to add an enclose, which is the inverse of this guy right here. And we're going to basically just take this whole block here. Boom. Boom. We don't need this parameter anymore, but we do need the device spec. And we'll look at our handy-dandy little reference over on the browser side. Again, go back into Interact. And if we go back, open, close, we'll see that this one here, dbyte's supposed to be 0. I need to fix that because there's no payload. But you'll notice that dstatS here is 0 because there's no payload. The command becomes C for close. There's no payload, so dstatS becomes 0. Dbuff also becomes 0, because it doesn't matter anyway. And so does dbyte, because we're not sending anything. Deox and Deox 1 and 2 are also 0. And in fact, we can actually optimize that a little bit by saying Deox is 0. And we can say in disable proc for the other side here so that the interrupts get disabled when the connection gets closed. Finally, we call it enclose. Now, you'll notice what I'm actually going to do here is I'm going to modify this ever so slightly. become so that we can use here we go. So, and finally again. So we have open and close. Let's go ahead, do a nice little check over here to make sure that we're good. Bam, bam, bam. Okay. See, looks good to me. And if we look down here at the bottom here, we have our little open and close tester to make sure that we're good here. Save the file. Go into the monitor, compile the result. We realize, oh, there's something goofy going on here. Probably because, let's see. Yeah. I noticed that a moment ago. I'll go ahead and save that because that needs to be saved anyway. Compile, and with a little run here, we open the connection and we close the connection successfully. Here we go. Turned off the wrong thing. There we go. Yes, you can definitely see that I am literally doing all of this live. It makes things challenging for sure. So there's in open, in close. And we've got in status, which essentially means we're left with two functions left to do what we need for reading and for writing. So we'll go ahead and, yeah, we'll borrow this guy as a little blink. We'll borrow this guy, sure. And we'll use him as a template down here. The description's different, so and this needs a couple of parameters that we don't already have. In addition to the device spec, we also need a destination buffer, and we need the number of bytes to read. This is absolutely important because since we're doing low-level communication over SIO, and because the payloads are fixed, we need to specify how many bytes we want to read ahead of time. This is why the status command is so useful, because the status command will tell you how many bytes are sitting waiting in the receive buffer of the FujiNet device, ready to be brought over to the Atari. So ds buff len. Great. Buff, and then finally a card for len. Boom. All we need here, read. And since this goes to the Atari, it's dstat S40. I'm not bringing up the website here because hopefully you're following along on the wiki here, and I want to put all of the screen here. Dbuff needs to point to our buffer that we specify on the arguments. 30-second delay, and then because we need to specify how many bytes we want to pull, and it's not predetermined at the peripheral side, we need to specify the number of bytes that we want to pull in length, not only in the dbyte here, which gives us the payload size, But we also need to sacrifice our 2 aux bytes to hold the length as well. We call here, and then we do in get error. Read, bang, 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 bang. Okay, good. Very good. Now we take and change this to in read, and I think we're good here. We go ahead and save. Go ahead and compile. Everything's looking good so far. Awesome. Okay, now let's go ahead and just jump right to it. Boom. And boom. And we're going to change all the instances of read to write and flip everything over the opposite direction. Again, same pattern. DS, there we go. And instead of R, it's W for write. This goes to the... I keep wanting to hit shift there on accident. Oh, come on. Did I change the wrong one? Damn it. No, I didn't. Okay, good. Okay. The to FujiNet. This needs to become 80 because the payload direction changed. Destination buffer, same pattern here. We get an error there. And that's everything that we need for our NIO library. Done. And because we're now done with this, I'm going to go ahead and go back, remembering to uncomment out these bits of code that I blocked out in both in open and in close. Because they're now ready for use, because we want to be able to turn on the interrupts automatically. There we go. Bam, bam, bam. We're all good to go. We write out the file. And we go ahead and try to compile it just to see. All good. There's our completed library. We can actually jump out to DOS real quick to have a look. And we can see that the source code for this library, excuse me. Let's go to drive 2 here. Hold on. We can see that the source code for this library takes up 17 double density sectors. Okay. And just for the sake of it here, we're going to copy to the printer for source code output. Okay, so now within that, we can come back into here, and we have a nice clean slate ready to write the second part of our program. Now that we've written our library, and now that we're reasonably sure that the library actually works, I didn't test the read and write functions directly, but I've already written this. I know that they work. And because of the interaction of the interrupt routines and how how action tends to clobber them when you go in and out of the monitor, I opted not to test them here while I was recording. So just trust that they actually do work. But you should try to test them writing simple bits of code to make sure that they actually function as expected. I'm literally working off of already existing nodes here. So with that, now we write a simple little program which uses this network library to do something interesting. Hold on a second while I actually prepare my notes here to make sure that everything's okay. Come on. Okay, here we go. And now we start with the simple Netcat program. A simple Netcat program. All this does is, at least from the user's point of view, provides a simple terminal between two network hosts. There's no telnet processing, and the only reason for that is simply because I don't have a protocol adapter for telnet on the FujiNet. Once that's in place, this program can be used as a telnet client with all of the escape codes that telnet can process. For now, you can use this for raw sockets, like for connecting to BBSs and stuff. It works just fine. So to start off with, again, we have a header. And we have an author, of course. I keep wanting to use PC key layout here. I'm so used to it. And that's it for the top of it. Nice and simple. And we're going to use our next new keyword here. And this is a preprocessor directive. Just like define was a preprocessor directive, there's one called include, which causes the compiler to include the source code for something that you've written, as if you had literally loaded it directly into the editor here and compiled it like that. So in our case, we'll include our NIO library. And now we'll actually start the module in earnest. And because we started NIO act with module, and because we're starting this with module, Action knows that these pieces of code are separate entities, and therefore can have separate global variable sets that will get added together, but it knows that there's a block of global variables in NIO, and it knows that there's a block of global variables in our main program here. The first one that we really need is bytes waiting. And we'll have that point directly to O2EA. And actually, since we already have that defined in NIO, we can literally say this. And we can have a key press variable to check for the current key press. This is an operating system routine, an operating system variable that gets set 60 times a second as part of the vertical blank to indicate the last key that was currently pressed. We'll need this. It will come in handy, very careful, very, very soon. We have a byte array for a device spec. We have, of course, the translation byte for the current translation mode that we want to use. We have a byte for what we call local echo, which we'll implement here in just a moment. we have a byte for whether or not the program is running or not. I can't remember exactly if I use this or not, but I'll keep it here anyway. And finally, we have a variable for the receive buffer. We have plenty of space for it, so we'll just say a large 8 kilobyte receive buffer. Furthermore, we now have, in addition to that, a couple of defines which will help us out here. We need to use CIO for one thing, and that's reading from the keyboard. And we use channel number 2 for that. And I'll define a couple of nice things for true and false. Make sure everything's good here. We'll go ahead and save that as nc.act. Write that out. All good. We'll go ahead and compile that. And we'll notice a change in behavior here. Now that we are including action files to be compiled, it will actually take and compile and stream in the included file. And you'll hear a difference between compiling any external stuff through include versus compiling what's currently in the editor buffer. You'll see here that it took and loaded in, streamed, and compiled out the result for NIO, and then it switched back to the editor when it was done doing so, and the file that was in the editor. So far, so good. Now we need to make a function to prompt for our URL. This is our first little function here, prompt for URL. And this is pretty straightforward. Give it a prompt. And we're using a string input here. And we're going to go ahead and put an end character here. And grab the second bit, which is our translation mode. Input B. And finally, our third prompt, which is our, let's see, input B, okay. And then local echo, whether or not we want local echo for on or off. And for simplicity's sake, I use 0 or 1 for this. It means I can process this a lot simpler. I could use yes or no for this, but I would have to use an if statement for this. That's okay. Local echo becomes this. Bam. Done, done, done. So that is the essence of our get URL function, which provides the user interface for our program. Let's go ahead and make our test harness for this. we can go ahead and call that, and then once we do that, we can literally just do this right here, and there's our test. So I guess there's not a print SE. No big deal. It's just there's literally forgot how to do this. Nerd. Anyway, excuse me. Is it print S? Print E, print S. Yeah, maybe it's something like that. Let's see. I know printf has it here, so let's have a look here. So let's say S E. So there we go. Let's test that out. Let's run that. Netcat, enter device spec. Translation. We want that to be that, and we want, yeah, sure. So there we go. Looks like our test works just beautifully. Bam. Great. Awesome. Okay, so there's our test harness. We might keep this open, we might not. We'll see how it turns out here. The next thing we need is the routine to handle the Netcat output. And that means when we receive characters from the keyboard, we need to send them to the output socket. And because of the way this actually is implemented here, I'm having to do it this way here. If you guys know a better way to do this, then go for it. We need an output for the output characters. And since we have a variable pointing directly at the last key pressed here, we can simply register it. If the key press is FF, then it means nothing has happened. Then we can return, and that's the end of the story. Otherwise, the character that we get is the result of IOCB. This IOCB will be opened up when the NC function starts. So this will already be opened by this point. So now we have our character in here. If local echo equal 1, then we go ahead and put out that single character to the screen as well. Otherwise, we go ahead and we do a write to the network socket. Single byte. Finally, we check to see if there was an error of some sort. We print write error. Print BE error. Then running equals false. we're no longer running, the program is no longer running, so will break out of the main loop that we're going to see in just a moment. There we go, FI and return. We save this. We go ahead and compile this to make sure it's okay. We go ahead and run the result. We can't, well, no, there's no test, so never mind. So this is good. There's our NC output. Conversely, here is our input. This handles data coming in and displaying it to the screen. Again, much the same pattern here. Being careful not to press the inverse key. Again, byte error. And this time we need a variable to hold on to an index that we're going to use. And I'm using I for index card here. That's cool. I, sure. And first and foremost, because we have this interrupt-driven method happening, we can check this single variable trip to make sure if anything's happening. If trip is equal to 0, then nothing is happening, and we can simply return and leave the rest of this routine alone. And this is absolutely important because every single time that we do an end status, that essentially means that we basically are doing an SIO poll. So imagine that happening many hundreds of times each second. You're just going to hear just this raspberry mess over your speakers as the SIO line is constantly being polled. So the interrupt routine, so the interrupt lines, and everything that we've done infrastructurally wise to use those interrupts is all so that everything is quiet when nothing is happening. We can go ahead and do an end status. We can do an end status here, and if error for whatever reason, let's say if error is equal to 136, this means that there's an end of file, then we need to say we're done. We're done, disconnected, we're no longer running. So essentially, anytime I want the program to stop, because it's constantly looping through these blocks of code, I set a flag to indicate that we need to stop. And we can gracefully exit our loop. And we're done. That's it. That's all we have to worry about. We can do that. We can return. And all is well here. Finally, we go ahead and check, just as a sort of safety valve. If bytes equals waiting equals 0, then we might as well return anyway because there's nothing to process. So let's just go ahead and deal with that. Sure, no problem. However, we finally also need to check if bytes waiting is greater than 8192 for whatever reason. If so, then we need to take and clamp that off to 8192 so that we don't overflow the buffer. And because all of the character removal and additions happen on the FujiNet side, we don't have to worry about that here. We just want to make sure that our input buffer is large enough. Finally, we get down to doing the network read. And for that, all we have to do, read into our RX buff. dia in device spec, RX buff, and that becomes, and however many bytes are waiting for us to do so. That's it. Boom, good to go. And did I just do a C thing here? This works, and this is fine, because if you find yourself doing that, then that's fine anyway. Action sees that as a comment. It's obvious that Clint Parker was familiar with C, so just interesting serendipity there. So okay, we do the network read, and if again we check the error. Oops. Back. If error is not equal to 1, then something happened. What happened? Print the error. And finally, we return. There. And of course, we close off that FI right there. And that's the read error. If we get here, then we have data that has made it from the FujiNet side all the way over to the Atari, and it's sitting in the buffer on the Atari. It's gone from the buffer on the FujiNet, it's now in the buffer on the Atari, and now we can drain it and display it. And that we can do with a for loop, sure. For I equals 0, 2. Hold on, sorry, lost my place there for just a moment. Bytes waiting, -1. Now there's a reason for this, and that has to do with the fact that yes, the arrays are subscripted, but for loops in this fashion are less than or equal to. And we don't want an off by 1 error. So we start the loop function. And we drain it. All we got to do there is this. That's it. Boom. That's our display routine right there. Put it out to the console. And because I'm just using the standard console routines here, this will work if you have an XEP80 or if you're running a special software 80 column routine, whatever. It just works. Whatever. So, drain, display the RX buffer. And now that we're done with that, we're done with this loop, but we need to do one little bit of housekeeping here. And that's to reset the interrupt. So we can say that we're done servicing this interrupt. You can now send the next one. And the PIA will now signal the next one. We do that by clearing the trip flag so that it can be reset again. And by doing the same trick we did above in enabling the interrupts in the first place, by re-enabling by the OR, bitwise OR, the interrupt enable bit. Boom. We're ready. We're ready to go. And with that, there are our read and write routines. Pretty much. Bam. Let's build that and make sure that builds okay. All good? Looking good. Okay, what do we have left here? Finally, we have the main Netcat function itself. No parameters, just here we go, set things up, open the connection, and then start spinning in the loop until things change. So, start with this. We need, of course, a byte for error. And we need to first open our device spec. and translation modes that we selected in get URL. And again, we check for error. I don't have to do this, but I'm doing the case for consistency's sake. Print. Again, same goofy pattern. And yes, this could be refactored even more, but I'm doing this just for the sake of readability. Print BE error. Yep. And follow that up by return. Since we're not running yet, we just take and print the error and we're done. Okay, bam. Otherwise, we get here, the connection is now open. Running equals true. And with that, now we go ahead and open the keyboard. We're using the standard CIO routines that are available in Action. And again, so here we go. Open the keyboard for reading only. Keyboard IOCB is now open. And here's the meat of the program. Right here. All that initialization has led us to this point. You're going to laugh. While run equals true, do ood nc output, nc input. That's it. Right there. That's it. Done. Boom. That's the main part of the program. Okay. So, finally, if running is now false, it falls out of this, and we will now start cleaning up. First thing we do is we close the keyboard. And then we go ahead and enclose our device spec. And hopefully, I think that's almost it. I just need to, yep, that should be it. Boom. That's all we have to really do to clean up. We don't have to do anything with the interrupts or anything because that's all handled by NIO. So all we have to worry about are the things that we initialize over here, namely the keyboard IOCB and making sure our device spec is okay. So there we go. Compile that, make sure that's okay. Good. So far, so good. We're going to go ahead and save that just to get that in place here. All right. So now that leaves us with one final thing. Let's make sure this is okay. Return, 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 return. Okay. Somehow we got, yeah, okay, so okay, good. Make sure that I didn't mess anything up there. Okay. Finally, the main entry point for the program. Bam. Proc main. I just call it main out of my own convention. You can call it, I mean, you could call it Bob if you wanted to. It doesn't matter. Get URL, nc. Done. And with that, our program is done and should now work. And assuming that the gods have smiled down upon me nicely here, I am reading directly off my notes here. This should just work. It's bolstered especially by the fact that we tested as much as we possibly could, unit testing the library as we were creating it. But with this, we now pretty much have two major chunks of source code here. So without any further ado, now that I've saved it, I'm going to compile the result and run it. And looks like we're going to close out 2 hours quite nicely here. Run the program. We have our Netcat. CRLF, and yes, Cave Mush does need local echo. Moment of truth. And there we go. There's our Netcat. We can see who's playing, etc. And you can see it just works. And if I go ahead and quit, done, okay, we disconnect, which is kind of interesting. Okay, looks like a slight difference there because it was happening. Okay, never mind. So there we go. Bam, we're done. Okay. It took a second to disconnect, and I hit a return before it finished disconnecting. Anyway, so that works. It's functional. And as a matter of fact, right now, if I were to actually take and write this out, there would be a binary file ready to go. We could take and do write to D2, nc.com, and we would have a binary file that we could actually deal with. But it's not 100% done yet. We still need to do a couple little tweaks. The first thing we're going to do is we're going to add a little chunk we're going to add a little bit of code that the action manual recommends that you do so that OSA Plus and DOSXL don't run the command twice. We do that by just injecting an RTS right at the beginning of the program segment. Okay, we go ahead, we compile. And we go ahead and we write out the result to nc.com. Bam, good to go. And if I go ahead and go out into DOS, we'll see our completed program. And right now it's at 7 sectors. Now, the thing about what's happening here is that we haven't compiled in the action runtime yet. That's actually what I'm going to be doing next to complete all of this. But for right now, since I have the action cartridge in here, I can run this. And you can see it just works. Okay. Quit. And yep. Boom. Okay. Great. So far, so good. And actually, the reason that this is happening right here, this 136 right here, I have a funny feeling it's because I'm running under OSA plus 4.1. We'll see. I don't know. Maybe. But to finish this off, I am actually going to go ahead and mount some things in place. First thing I'm going to do is I'm going to fmount into drive 3 from my file server. the action runtime disk. And we're going to go ahead and run config. Since this is a single density disk, you need to let it go and do its thing, configure everything in. And we're going to go ahead and run ADOS to load Atari DOS 2.0 or the FMS 2.0 into place so that I can do this next command. I'm going to take, and if we look on drive A3, we'll see a whole bunch of example action code here. And we actually want sys.act, which is the action runtime. We're going to take and copy that over using the copy to fork command. So A3. I'm going to move that over to drive 2 as sysact. And there are all sorts of useful utilities on here. ST, for example, which will print out a symbol table. If you take and compile it into memory and then compile your project, you'll get a symbol table output on the printer. So with that, if we look on drive 2 now, we can see NIO, NCAct, and now sysact that we can reference. Groovy. Let's go ahead and go back into, I'm actually going to take and do a run E477 to clear out because I don't want ADOS in there anymore. Don't need it. We're done. We'll just reload. And now we will go back in, we will load NCAct. Make sure this is all good here. We're doing good. Okay. And we will now include the system runtime library, which will make this a completely standalone application. Go ahead and write that and compile it out. And we're done. Now we can write the finished result. And with that, we're done with action. We're just done. And for this, I will go ahead. We'll go back out to DOS. We'll see how much bigger the file is now that we've done this. And yeah, we've doubled the size of the binary because now we have the routines that were formerly being called in the cartridge now being directly linked into the target binary. But they're all here, and it's all completely self-contained now. I'm going to go ahead, and with this, I'm going to reset my machine while holding down the ultimate cart. And I'm going to exit out because I'm not going to put anything in here. My action cart is now complete, is not in the system at all. I'm not going to prove that by hitting car because it will hang. OSA Plus hangs if there's no cartridge. But we're going to go to drive 2 and we're going to run our Netcat application, our now completed Netcat application, and go to a couple sites. We'll start with good old Cave Mush. CRLF, local echo, yes, sure. And so on. We'll go ahead and quit. Done. Okay. Now closed off everything good. Now we're going to do that again. And this time we're going to go to bbs.fostex.net. Now, you don't have to put 23. If you don't, it uses port 23 by default. And we're going to use CRLF again. We don't need local echo for this. You'll see that we're doing just fine. Hammering right along. And rather than this happening through the Wi-Fi modem side of things, this is actually happening via the inside of things. And because bbsfostex.net has an unusual buffering technique, the jerks that you're seeing here are indicative of this particular host. And the fact that the end device is fetching these characters faster than Fostex is putting them out. So, no problem. Go ahead. Let's go ahead and log off. Boom. Okay. Finally, we'll do an Atari BBS just to do it. TCP. Now, it's worth noting that I'm just using the TCP protocol here. You can use any protocol that N supports. You could put HTTP locations here. You could look at a file on FTP using this. It just works. All of the details of protocol negotiation are handled by the FujiNet and automatically abstracted over. So the Netcat application is just really, really simple. No translation in this case, and no local echo. And I don't have my margin set, but it'll still be okay. I should have set the margin to 0 for this application, but that's okay. Oh, probably, yeah, I'm guessing that it's probably, yeah, my bad. Wrong host. Let's try that again. No local area. There's probably a couple of small little subtle errors that I did in transcription here, which are accounting for the slight bugs that I'm seeing, but no biggie. So here we go. Bam. Connected. Boom. Great. And here we go. Groovy. And yeah, margin's a little too big here, so you're seeing that happen. No big deal. All good. All good. Sure, let's check the latest messages. Message board number 1, sure. Nope. See? All good. So there we go, man. Boom. It works. It's just working like gangbusters. We'll exit here, we'll do goodbye, yes, leave, and we're done. Yeah. So there we go. From start to finish. Not only writing a binding for action, but also a demonstration program to use it. I know this video is long, but I hope you guys have watched it to the end and have found it informative and will use the knowledge that I presented here to push this to other languages as well. Until next time, guys. Have fun.